Hello, my name is Fernanda García. Today I'm going to explain my poster called Removal of Congo Red Dye using bioimide supports on silicon dioxide particles. This project will be exhibited on the CV Materials and Environment Symposium and the 13th International Material Research Congress. Aluminum is considered an environmentally friendly metal. In fact, aluminum oxyhydroxide has been well reported for environmental remotion, including absorption and photocatalysis. The aluminum oxyhydroxide, known as bioimide, has been used for remotion of heavy metal ions, dyes, and other pollutants. In this work, we report the synthesis of bioimide by two different approaches. One is direct precipitation, and the other is precipitation over silicon dioxide particles. The silicon dioxide was synthesized by the stopper metal, mixing tetraethyl orthosilicate with an ethanol water solution in presence of ammonium hydroxide. The silicon dioxide particles of 400 to 800 nanometers were disposed in an aqueous solution of aluminum nitride, and sodium oxydroxide was agreed to precipitate the aluminum oxydroxide. The result indicates that the direct precipitation conduces to a mix-up at diaspore bioimide and a mixed sodium aluminum oxide, while the synthesis over the silicon dioxide particles produces only bioimide crystal phase. Then, the bioimide and silicon dioxide particles were dispersed in an isopropanol alcohol and deposited on aluminum substrate by electrophoretic deposition. Finally, the coatings were used for Congo red dye remotion. This result suggests that bioimide by silicon dioxide particles can be successfully applied for environment applications. Continuing with the metals, the chemical thresholds were analytic grade purified without any further purification. For the direct precipitation metals, we prepared aqueous solution for aluminum nitride with 5% sodium hydroxide, then agitation for 0.5 hours, sequentially etched and agitation for 24 hours. The result solution was centrifuged and washed with ethanol. Then the solid was dried at 19 degrees Celsius for 44 hours. For the precipitation over silicon dioxide particles, we prepared aqueous solution for aluminum nitride with silicon dioxide particles. Then agitation for 15 minutes. Then we add 5% sodium hydroxide drop by drop, continues to agitation for another 15 minutes, sequentially etched and agitation for 14 hours. The result solution was centrifuged and washed with ethanol. Then the solid was dried at 19 degrees Celsius for 44 hours. Continued with the electrophoretic deposition, the result particles were dispersed in isopropanol alcohol and deposited on aluminum substrate by electrophoretic deposition at 12 volts for 20 minutes. We prepared a Condor red solution at 2 ppm. The absorption process was carried out in a UV-based spectrophotometer. In order to investigate purity of the aluminum oxydroxide, the product was measured using a FTR between 0 and 4,500 centimeters less ones. In the figure 1 shows the yellow spectrum, the letter A corresponding by precipitation direct and the letter B corresponding to precipitation over silicon dioxide particles. The strong brown bands and at 3,700 to 2,800 centimeters less ones is a signal to extraction privation of group in a hydroxide structure as well as in a physical absorption water. They showed that 1638 is taken for the behind mode for absorption water. The band location in 1300 to 1314 is corresponding to the neutral group strong bands, while the band at 1100 to 1200 centimeters ones is belong to has aluminum oxide hydroxide mode. The other band location is 750 to 600 to 30 below to the oxyhydroxide aluminum vibration mode. In the figure 2, we observe the different patterns of the letter A corresponding to the power obtained by direct precipitation. We observe the presence of planes coming from a different phase. The blue color belongs to signal of the gamma phase to emit. The red color corresponds to plane alpha phase to diaspora. Finally, the green color are characteristic planes for a sodium and aluminum oxide. Finally, difference phase tells us about a low purity in the power obtained. On the other hand, in the figure 2b, we can observe the diffraction patterns to precipitation over silicon dioxide particles. We observed only characteristic planes of gamma emit. We conclude that, using the silicon oxide particles of the nucleus, we had a great control in a phase. Addition to the emit range is directly transformed to aluminum oxide. In the figure 3, we observe the graph of concentration and concentration behind versus time for the absorption process of the particles obtained by precipitation over silicon dioxide particles. In it, we observed that the material was 35% absorbed. The first in the figure 4 corresponding to the place deposited material before and after the absorption process. The letter A corresponding to direct precipitation and the letter B corresponding to precipitation over silicon dioxide particles. This result suggests the emitted by silicon dioxide particles can be successfully applied for environmental applications. In figure 5 corresponds to a scanning electron microscopy of the particles obtained by precipitation over silicon dioxide particles. We observe a particle with a spherical morphology with a coating, which prevents the growth of the bohemite in the circulating particles. In conclusion, bohemite was synthesized by two different approaches, direct precipitation and precipitation over silicon dioxide particles, previously synthesized by the silver metal. According to the FGR and the XRD analysis, the direct precipitation method conduces to a mix of bohemite diaspora and a mixed sodium aluminum oxide, while the synthesis over the silicon oxide particles conduces only a bohemite crystalline phase. The electrophoretic deposition to bohemite in silicon oxide particles were used to Congo red daily remotion. This result suggests that bohemite particles can be successfully applied for environmental applications.